Let's step through this next one together because I'll show you a couple of hints. Let's find the inverse Laplace transform for 2s plus 5 over s squared plus 6s plus 34. Well, I notice here this linear term 6s, and so maybe what I want to do is complete the square there. So that would be a good thing to try. So s squared plus 6s, then we have plus 34, and we still have 2s plus 5 in the top. And to complete the square, we take our linear term, 6, half of that would be 3, squared would be add 9, but so that I can keep it the same thing, I'm going to subtract 9 all in that same expression. And when I do that, I'm going to get 2s plus 5 over s plus 3 squared plus 25. Ooh, that's nice. 25 is a perfect square. We've still got a small problem though. This is 2s plus 5, but this is s plus 3. So if I were to double s plus 3 so that it kind of made the top look like what's being squared here in the bottom on the cosine, I'd need 2s plus 6. I don't have 2s plus 6, but just like we did with completing the square, what if I add 1 and subtract 1 to that expression? Now I've got 2s plus 6, but the cost is I still have a minus 1 now, over s plus 3 squared plus 25. But this guy can break down and will be a lot easier to handle because I can write this as 2 times s plus 3 over s plus 3 squared plus, and to help us notice the pattern, I'll call 25 5 squared. And I'll just break this fraction up into his two pieces on the numerator there, minus 1 over s plus 3 squared plus 5 squared. Now this guy, if you factor out the 2, looks exactly like this one here, with a is -3. So the s minus a -3 would be s plus 3. And the 2 will factor out because of the definition of the Laplace transform. This one's looking closer to something we recognize, but there's a small problem. We would need a 5 in the top. Well, when we don't have something that we need, we make it. So let's times by 5 and 1/5 and see what we've got now. So we've got literally 2 times s plus 3 over s plus 3 squared plus 5 squared minus 1/5 times 5 over s plus 3 squared plus 5 squared. And these guys now look like things that we recognize. So let's do the inverse Laplace transform on those guys. So s plus 3 over s plus 3 squared plus 5 squared. We know that inverse Laplace transform, that's going to be e to the -3t times cosine of, remember that this guy tells us what the argument of the inside the cosine is going to be, so cosine of 5t, and our other piece, the inverse Laplace transform of 5 over s plus 3 squared plus 5 squared. We recognize him, put him into a format that we know, so that is going to be e to the -3t times the sine of 5t. Therefore, when we do the Laplace transform on this guy, we're going to get 2e to the -3t times cosine of 5t minus 1/5 of e to the negative 3t times the sine of 5t. So this guy, when we do his inverse Laplace transform, gives us that answer right there. Okay. All right, so let's try an initial value problem with this. So let's take and solve the initial value problem. 2x double prime plus 3x prime minus 2x equals 0. And we've got initial conditions of x of 0 is 0 and x prime of 0 is negative 2. And as a little bit of a help, remember that the Laplace transform of x of t is capital X of s. Laplace transform of x prime of t is s capital X of s minus x of 0, which in this case is 0. So this just gives me s times capital X of s. And the Laplace transform of x double prime, which is as far as we need to go, is s squared capital X of s minus s x of 0, which that piece is 0, minus x prime of 0, which is negative 2. So we'll get s squared capital X of s minus a negative 2, which is plus 2. And our Laplace transform of 0 is 0. All right, so if we do the Laplace transform of this whole differential equation, we're going to get 2 times x double prime, which is s squared capital X of s, plus 2, plus 3 times x prime, which is s times capital X of s, minus 2 times x, whose Laplace transform is capital X of s. And that is going to equal the Laplace transform of 0, which we know to be 0. All right. Let's distribute and see if we can't collect on the X of s term. So 2s squared capital X of s plus 4 plus 3s capital X of s minus 2 capital X of s is equal to 0. Let's subtract 4 and then factor out the capital X of s. So we'll do 2 baby algebra steps in 1. Okay. And therefore we find out that capital X of s is negative 4 over 2s squared plus 3s minus 2. And if we're careful, we notice that that denominator even factors. Let's see, so that'd be 2s and s to make 2s squared the easiest way possible. We're going to need let's see, negative 2, so that it adds up to be a 3. 2 times 2 is a 4, and a minus 1 would work. So we're going to need to take this guy and break him into partial fractions. Okay. All right, let's see what we get then. Our next step in partial fractions would be that negative 4 is equal to a times s plus 2 plus b times 2s minus 1. Once we get a common denominator here, and if the denominators are all the same, then the numerators must be the same. And with a little bit of substitution here, let's say that s equals, we'll start out with s equals 1/2. If s equals 1/2, this term goes to 0, and that allows me to find the a guy. So we've got 1/2 plus 2 is 5/2. So negative 4 is equal to a times 5/2. So if we times both sides by 2/5, we find out that a must have been negative 8/5. Okay. Similarly, if we let s be negative 2, we'll find out that negative 4 is equal to b times Negative 2 times 2 is negative 4 minus 1, which is negative 5. So B must have been a positive 4/5. Uh-oh, we're pushing our 10-minute mark, so I'm going to pause here and we'll pick up in the next video.